Radical Reactions, Chapter 10. Objectives: 1. Radicals and geometry. 2. Homolytic bond cleavage. 3. Reactions and mechanisms. 4. Polymerization. 5. Radicals and nature. Your goals. By the end of the chapter, you should be able to understand radical formation and radical geometry, write radical reaction mechanisms, predict reagents needed for a target product, predict products given the reagents. 1. Radicals and geometry. Organic radicals contain unpaired electron and are neutral because they have a formal charge of 0. Consider these radicals here, where we are going from the methyl radical all the way to the tertiary radical. The carbon that we're going to calculate the formal charge for normally has 4 valence electrons when it is neutral. We also have 1, 2, 3 bonds and 1 electron. If we take the calculation 4 minus 4, we see that we have 0 as a formal charge. Even though the formal charge is 0, it is still electron deficient due to the incomplete octet. Radicals follow the same stability as carbocations, as they are both electron deficient species. The bond strength is inversely proportional to the carbon radical stability. The more stable the resulting radicals, the weaker the bond. For example, if we have a methyl, the CH bond has a bond energy of 435 kilojoules per mole. When we consider the CH bond of a tertiary carbon, it is now 381 kilojoules per mole. Resonance stability. Radicals like carbocations are stabilized by resonance delocalization. We may still see the allylic position, and in this case, instead of having a carbocation, we have a radical. We use fishhook arrows to present possible resonance forms. The fishhook arrow represents the movement of 1 electron instead of a pair of electrons. Note that this radical electron here can come in and form a pi bond with one of the electrons of this pi bond, while the other electron becomes a radical. The more resonance delocalized a radical is, the more stable it is. Benzylic radicals are more stable than allylic radicals because the radical is delocalized over more carbons. We have more resonance structures that contribute to the true structure. Resonance stabilized radicals are more stable than a tertiary radical. And we can see that in terms of bond energies. It's even lower. The lower the bond energy, the more stable it is. Vinylic radicals are unstable. They're especially unstable, as with vinyl cations, because the radical is in an sp2 orbital, and that is less stable than having a radical in an sp3 orbital. Geometry of radicals. Recall the orbital hybridization in carbocations and carbanions. In carbocations, we have an empty p orbital and the carbon is sp2 hybridized. In carbanions, the carbon is sp3 hybridized with a lone pair of electrons in an sp3 orbital. Radicals appear to be trigonal-planar sp2 hybridized or shallow trigonal pyramidal sp3 hybridized, tetrahedral in terms of our electron geometry. So note either trigonal-planar or a shallow pyramid rapidly inverting. Whether the free radical carbon is an sp2 or rapidly converting sp3, a reaction will occur on either side of the plane with equal probability. If a chiral center forms in the product, a racemic mixture will be obtained. 2. Homolytic bond cleavage. Free radicals form when the bond breaks homolytically. Homolytic bond cleavage means that the bond between XY breaks evenly, giving 1 electron to X and 1 electron to Y, forming the radicals. Note again the single barbed or fishhook arrow is used to show that electron movement. We have used a full arrowhead to show 2 electrons moving, and now we're going to use a fishhook arrow to indicate 1 electron is moving. 3. Reactions and mechanisms. Like ionic mechanisms, radical mechanisms follow patterns. But radical mechanisms are distinctively different. For example, radicals do not undergo rearrangement. Radical mechanisms will follow 6 key arrow pushing patterns. The carbocation we have seen in the past will rearrange to form a more stable carbocation, but this radical will not rearrange and form a more stable radical. Key patterns. 1. Homolytic cleavage. It is initiated by light or heat, and that will result in 2 radicals. 2. Addition to a pi bond. A radical may react with the pi bond. If this is alpha carbon of the pi bond, it can make a sigma bond between the radical and itself, while the radical is now formed on beta carbon. 3. Hydrogen abstraction. This is not the same as a proton or H+ transfer. Rather, it is H with 1 electron making a bond with a radical, resulting in the release of a new radical. 4. Halogen abstraction. A diatomic halogen may undergo a reaction with the radical, resulting in a halide radical. 5. Elimination. This is the reverse of addition. The radical on the alpha carbon is pushed toward the beta carbon to eliminate a radical atom or group. 6. Coupling. This is the reverse of homolytic cleavage. 2 radicals react to make a sigma bond. May also view as group the 6 relationships among these 6 patterns, and you will see there are only 3 processes, the forward and the backwards. If we have a sigma bond, it may undergo homolytic cleavage to form 2 radicals. The 2 radicals may couple to form a sigma bond. A radical may add to a pi bond, or a radical may undergo elimination to form a pi bond and release another radical. A radical may undergo hydrogen abstraction with something that contains H. It can go in the reverse direction via hydrogen abstraction as well. Steps in mechanism. The steps in a radical mechanism are classified as either initiation, termination, or propagation. An initiation step is one where a radical species are formed from a non-radical species. That means homolytic cleavage has occurred. We have a sigma bond, non-radical species here, that homolytically cleaves to form 2 radicals. Propagation occurs when a radical reacts with a non-radical species to form a new radical and non-radical. Propagation steps include addition to a pi bond, hydrogen abstraction, halogen abstraction, and elimination. Termination occurs when 2 radical species react to form a non-radical species. We saw that with coupling. Let's consider the chlorination of methane. Chlorination of methane follows a radical mechanism, where methane gas undergoes a reaction with chlorine in the presence of light to form methyl chloride and HCl. Initiation. Chlorine radicals are created. Chlorine undergoes homolytic bond cleavage to form 2 chlorine radicals. Propagation. These steps are self-sustaining. The first propagation step consumes the chlorine radical, and the second step produces one. This is hydrogen abstraction, for example. Here is halogen abstraction. Termination. This occurs when the radicals themselves collide or couple. We can have coupling of 2 chlorine radicals, the coupling of a methyl radical and a chlorine radical, or the coupling of 2 methyl radicals. Chlorination via radical mechanism. With substrates more complex than ethane, multiple monohalogenation products are possible. 2 monohalogenation products are possible for propane. There's either going to be the secondary alkyl halide that forms or the primary alkyl halide. The secondary alkyl halide forms about 60%, the primary about 40%. With chlorination, there's a significant amount then of each product. But since the secondary radical is more stable than primary, the secondary halide is the major product. Note that with hydrogen abstraction, in terms of mechanism and potential energy, the secondary one is much more thermodynamically stable and has a lower energy of activation. Hydrogen abstraction from a secondary carbon will occur a lot faster than the primary carbon. We have here 2 hydrogen atoms and then 6 hydrogen atoms here, but this is going to occur a lot faster. The net reaction. The sum of the propagation steps gives the net reaction. For example, taking the hydrogen abstraction, the halogen abstraction, we end up with this net reaction here, the chlorination of methane. Propagation is a chain reaction. The products for a later step serve as a reactant for an earlier step in the mechanism. Polychlorination is very difficult to prevent. In other words, we may get monochlorination, but the di, tri, and tetrachlorination is also possible. Methyl chloride is more reactive towards radical halogenation than methane. We need an excess of methane then relative to the chlorine so that the monohalogenation product is the major product. Radical halogenations. Fluorination itself is so exothermic it is not practical due to how violent it is. Halogenation is endothermic, meaning it's not thermodynamically favored and doesn't occur. Only halogenation with chlorine and bromine are useful. In terms of their favorability, they are thermodynamically favored and they're not too violent. Both chlorination and bromination are exothermic. But delta H for the first step of bromination itself is endothermic. Bromination. Bromination is much slower than chlorination. Note the energy of activation for the rate-limiting step in chlorination has a much lower energy requirement compared to bromination. Bromination is much more selective for the more reactive secondary carbon. If we have, for example, propane, we will get the 2-bromopropane at 97% versus 3% of the 1-bromopropane. Bromination at a tertiary position happens 1,600 times more often than a primary position. So while chlorination would give us a significant amount of both products, take a look here, we would pretty much get 100% bromination at a tertiary position. For example, in the halogenation of S,3-methylhexane, the chiral center is the most reactive carbon in the molecule. The chiral center is a tertiary carbon and has a weaker CH bond than secondary and primary carbons. A racemic mixture would be obtained. Now let's consider the radical addition of HBr. We learned that HX will add across a double bond with anti-Markovnikov regional selectivity in the presence of peroxides, or ROOR. The peroxides initiate a radical mechanism of addition. This is a different mechanism and different selectivity. The reaction is initiated by thermal homolysis of a peroxide, which then initiates a formation of a Br radical from HBr. The Br radical then in theory could add to either side of the alkene. Here is the initiation steps, the formation of the radicals. And here is the Br radical potentially adding to either side of the alkene. But it will add to the side that generates a more stable carbon radical, as that will be the lower energy intermediate and thus a lower energy transition state. So here we have a tertiary radical, here we have a secondary radical. The tertiary radical is more stable and it is favored. Radical addition of HBr continued. The Br radical adds to the less substituted carbon of the alkene, generating a more stable or more substituted carbon radical. The carbon radical then abstracts an H to form the product, and the propagation of the chain continues. Here is propagation steps addition and hydrogen abstraction. Most of the radicals in solution at any given moment will be Br radicals, so combination of them is typically the termination step. But the combination of any two radicals still makes a termination step. We can have coupling of two Br radicals, and we can also have coupling of two other radicals. Anti-Markovnikov radical addition of HBr is generally spontaneous, or the product is favored. Note that the radical addition of HCl and HI are generally non-spontaneous, and the reactant is favored. Allylic halogenation. Recall the weakest CH bond, or the lowest bond dissociation energy, will undergo radical H abstraction faster than others. Alkenes selectively undergo H abstraction then at the allylic carbon. H abstraction of an allylic H results in a resonance-stabilized allylic radical. Bromination of an alkene is selective for allylic carbon. Here we have allylic halogenation. We have an alkene, bromine in the presence of light, resulting in allylic halogenation. But note, addition of the bromine to the alkene itself is a competing reaction. Solution, NBS. To avoid the competing alkene addition, NBS is used as a source of Br radicals instead of using Br2. That's N-bromosuccinimide, or NBS, shown here. In the presence of light, we end up with the stabilized species via resonance and a bromine radical. Using NBS keeps the concentration of HBr and Br2 low, so competing addition reactions to the alkene are minimized. Propagation produces the allylic radical in HBr, as we can see here. The HBr produced reacts with NBS to form Br2, and this Br2 continues propagation and the formation of the product. With asymmetric alkenes, a mixture of isomeric products are often obtained. So note, we would get a mixture of products here with this asymmetric alkene. In the presence of NBS and light, we end up with different halogenated products. The radical is delocalized on two carbon atoms, so halogenation occurs on either site. Utility. Chlorination is oftentimes used to synthesize alkyl chlorides, and it's only useful when there's only one possible product. Bromination is more selective and is slower, and can be performed when several monohalogenated products are possible. Overall, the real advantage of halogenation is functionalizing an otherwise unreactive alkane, which can then be converted to other useful functional groups. And here's an example of using NBS and alkane to form a halogenated compound, and then this compound can undergo substitution, elimination, and then to other products. Initiators. Radical initiator. This possesses a weak bond that cleaves homolytically with heat or light, just like we saw with halogens or dihalides. Alkyl peroxides can also undergo cleavage. Acyl peroxides can also undergo cleavage. And the acyl peroxide is the most reactive It is effective at 80 degrees Celsius. Inhibitors. Radical inhibitors will react with radicals and prevent a chain process from initiating or propagating. Stabilized radicals and compounds that easily form stabilized radicals are good inhibitors. Oxygen is a diradical and will react with two other radicals. Hydroquinone will also react with two radicals. Radical reactions are very slow in the presence of oxygen. Hydroquinone undergoes H abstraction to form a resonance stabilized radical. Here are a couple of examples. We have hydroquinone reacting with a radical via hydrogen abstraction, and now this is resonance stabilized. Hydrogen abstraction of the resonance stabilized species with another radical can produce benzalquinone. 4. Polymerization. Free radical conditions are also frequently used to form polymers. Ethylene, for example, can undergo polymerization to form polyethylene. Polymerization process joins together many small units called monomers in a long chain. Radical polymerizations generally proceed through a radical chain mechanism. There's initiation that occurs, followed by propagation, and then termination or the coupling. Uses of synthetic polymers. Polymers with varying properties are obtained by polymerizing substituted ethylene derivatives, such as vinyl chloride, styrene, propylene, and tetrafluoroethylene, resulting in uses that we see in everyday life, from PVC plumbing to carpets to tires, televisions, radios, styrofoam, etc. Key reactions. Radical reactions are synthetically useful and will be applied to multi-step syntheses throughout this text and course. Bromination of alkanes, allylic bromination, anti-Markovnikov addition of HBr to alkenes. Recall major purpose is to add functional groups. So once we have a halogenated alkane, then it can undergo substitution and elimination. 5. Radicals and nature, the atmosphere and ozone. So the next few slides are going to be for your information only, but you should know how radicals occur in nature. Ozone is both created and destroyed in the upper atmosphere. We have ozone interacting with light from the sun and heat from the sun, resulting in oxygen in a radical, and then that can undergo termination to form ozone again, and this is a very cyclic process. UV radiation is converted to heat. Heat is more disordered form of energy. This process is spontaneous because entropy is increased. O3 depletion is a serious health and environmental problem. Without O3, harmful UV radiation then penetrates the atmosphere. Chlorofluorocarbons are believed to be the culprit. They reach the upper atmosphere, react with UV light to form chlorine radicals, then radicals destroy ozone. Cl radicals also form during propagation and continue the destruction of ozone molecules. Here is the initiation step and the propagation step, and there are different CFs. CFCs have been replaced with hydrofluoroalkanes or HFAs. They are sometimes called hydrofluorocarbons, and these are the species as examples that have been replacing the CFCs. They are not as harmful as CFCs because they don't produce chlorine radicals, but they still act as greenhouse gases. Autooxidation is the process by which organic compounds react with atmospheric oxygen to form a hydroperoxide. This process is generally very slow. Ethers are particularly susceptible to autooxidation. A diethyl ether can undergo the formation in the presence of oxygen to a hydroperoxide. Hydroperoxides can be explosive, and so ether supplies cannot be stored for long periods of time. Storing sensitive compounds in dark containers prevents light from accelerating the process. Triglycerides are important to a healthy diet, but are also susceptible to autooxidation, or allylic carbons are especially reactive. So here's an example of a triglyceride. Autooxidation causes food to become rancid and toxic. Foods with unsaturated fatty acids have a shorter shelf life unless preservatives are used. These preservatives are radical inhibitors and are often called antioxidants, or are radical scavengers. Examples include BHT and BHA. One molecule of BHT can prevent thousands of autooxidation reactions. Natural antioxidants prevent the oxidation of cell membranes and other biologically important compounds. A couple of examples include vitamin E and vitamin C. Vitamin E is hydrophobic and finds its way into cell membranes, while vitamin C is polar and functions in polar mediums such as blood.